The effect of transistor sizes on the transient response in CMOS, in NMOS logic. In NMOS logic, the correct choice of the sizes of the transistors was necessary for the gates to work. This is not necessary for typical CMOS logic to operate functionally correctly. However, as was mentioned, the ratio of W by L's of the PMOS transistors to the W by L's of the NMOS transistor does not affect the gate threshold voltages, and more importantly, the transient response. There is no exact optimum ratio for the size of p-channel transistors to n-channel transistors that can be specified independent of the application. However, there are two situations in which here you can see the figure. Here you can see the figure: a CMOS inverter driving two identical inverters. Something can be said about the relative W by L's. Something can be said about the relative W by L's. The first case is when a single gate is driving a number of identical gates. Consider the situation shown in figure, in which a CMOS inverter is loaded by input capacitance of two identical inverters. This example is to be analyzed for the transient response. For the transient response times of the first inverter, it is assumed that all n-channel transistors have identical W by L's. Also, all p-channel transistors are assumed to have the same W by L's, but these may be different from those of the n-channel transistors. This situation is representative of many typical situations encountered in a CMOS design where the fan out is small. When considering the transient response of the first inverter, it is first necessary to approximate the capacitive load. There are two components to this load. The first is the junction capacitance of the drains of Q1 and Q2. These capacitances are roughly proportional to the widths of Q1 and Q2, assuming Q1 and Q2 are not too large. In addition to the capacitances due to driving the inverters 2, 3, the capacitances of these inverters consist of principally the gate capacitances of n-channel transistors of two n-channel transistors and two p-channel transistors. The exact wave and the widths are large. The transistors are realized by multi-finger structure that minimizes the junction capacitance as described in chapter. Determination of these capacitances is a difficult and highly non-linear problem, but fortunately conservative estimates can easily arrived at using equation of chapter, which is repeated here. When the fan transistor is hard and in the triode region, its gate channel capacitance is approximately given by CGS equal to WLCOS. The equation we find the capacitive loading of the two inverters is approximately given by CL equal to 2C C0 x LWN plus WP, assuming the N and P channel transistors have equal lengths, which are also chosen to the minimum length, equal to the minimum length. Thus, these input capacitances are also proportional to the widths of the transistor, assuming all transistors have equal minimum lengths. Then scaling widths of all the transistors equally. Both N and P channel has little effect on the transient delays. This is because as the widths go up, the capacitive loads go up proportionally, but the equivalent resistances go down inverse proportionally to the rise and fall constants roughly unchanged. This this is exactly true for very small widths in which the junction wall capacitances uh, become more important, causing larger delays. It also ignores varying capacitance and external capacitances. When these become important, higher transistors result in smaller delays. However, for the simple case being considered, the capacitance of the delay on the scaling of all transistor widths is a reasonable approximation. Thus, it is necessary to optimize the delay only as a function of the ratio of the W by L of the P channel transistors to the W by L of the N channel transistors. If a number of gates are in series with no memory or local feedback, that is acyclic logic, then the average of the rise and fall times determine the overall gate delay. This might be the case for flip-flops or pipe logic, but will be the case considered now. Also, only the load capacitance due to the gates being driven will be considered. If the junction capacitance is also considered, the conclusions would change very little, but the analysis would be more complicated. The extra complication is felt to the is not felt to be merited by any substantial increase in insight. The average of the rise and fall times of the first inverter of figure is TAV equal to 1.2 CL equal minus 1 plus R equal minus 2 by 2, where CL is given by equation and R equals to 1 and R equals to R given by equation and equation respectively. Therefore, we have TAV equal to 1.2 into 2 C naught X L W N plus WP 1 by 2 2.5 by nu N C naught X W N by L VDD minus TA VTN plus 2.5 nu P C naught X WP by L VDD minus VDP. You can see the equation. Assuming VDD minus VNA is equals to VDD plus VTP, and rearranging, we have TAV equal to 3L square by VDD minus VTN nu N plus into 1 plus WP by WN into 1 plus N plus nu N WN by nu P WP. To find the optimum nu P by WN, minimize the average of the rise and fall times. We can differentiate equation with respect to WP, and WP by WN, set the result equal to 0. Solve for WP by WN continuous. After some algebra, we have dou TAV by dou WP by WN equal to 3L square by VDD minus VTN nu N into 1 minus nu N by nu P Wn by Wp whole square, setting equal 0 to the optimum Wp by Wn as Wp by Wn opt is equal to root over nu n by nu by nu p. For example, if nu n by nu p equal to 0.5, optimum ratio for Wp by Wn is 1.5 is 1.58. This is the reason for the earlier statement in session that a ratio of Wp by Wn is equal to 1.5. It is usually reasonable choice. For this choice we have TAV equal to 3L square ED minus VTN nu n into 1 plus root over nu n by nu p whole square. It is interesting to see how the average rise and fall time increases the speed, increases the special cases. Wp by Wn, Wp by Wn is equal to 1 and Wp by Wn equal to nu n by nu p for Wp by Wn equal to 1, and using the equation we have TAV equal to 6L square by VDD minus VTN by VTN nu n into 1 plus nu n by nu p. Also for Wp by Wn equal to nu n by nu p, we have TAV equal to 6L square by VDD minus VTN nu n into 1 plus nu n by nu p. Which is identical to equation. For example, if nu n by nu p is equal to 0.5 typical value, using equations we can see increase in the average of the rise and fall times by 5%. This is very small. Increase indicates that that half an optimum exits taking Wp by Wn equal to 1 would cause little penalty and would save space. This choice is often used except more in critical design. It would be emphasized that the preceding analysis ignored any writing capacitances or external taking. The p-channel wider definitely improves the rise time, and therefore the average of the rise and fall times in this stream. Designers often take Wp by Wn equal to 2 or 3 as a compromise for when the load of the gate is not known. The reasonable choice might be Wp by Wn equal to 1.5. The constant term in equation, that is the term P prox equal to L square by VDD minus VTN nu n. It is independent of geometry. And dependent only on the technology. It is good figure of merit when comparing to different technologies. Also, it makes it obvious important short channel lengths and for high speed operation. Thank you.